Good day, this is Professor Will, CBMD PhD. Today's Wednesday, June 23rd, 2021. It is 8:23 and 14 seconds p.m. Eastern Standard Time. Today's research, organic semiconductors. And don't forget to check out my website. So let's hop to it here. Tuning the energy gap, a novel approach for organic semiconductors. Date June 10, 2021. Source Technische Universität, Dresden. What is already established for inorganic semiconductors stays a challenge for their organic counterparts. By tuning the energy gap, by blending different semiconducting molecules to optimize device performance, now scientists demonstrated how to reach this goal. Organic semiconductors have earned a reputation as energy-efficient materials in organic light-emitting diodes, OLEDs, that are employed in large area displays. In these, and in other applications, such as solar cells, a key parameter is the energy gap between electronic states. It determines the wavelength of the light that is emitted or absorbed. The continuous adjustability of the energy gap is desirable. Indeed, for inorganic materials an appropriate method already exists, the so-called blending. It is based on engineering the band gap by substituting atoms in the material. And this allows for continuous tunability, as for example, in aluminium gallium arsenide semiconductors. Unfortunately, this is not transferable to organic semiconductors because of their different physical characteristics and their molecule-based construction paradigm, thus making continuous band gap tuning much more difficult. For inorganic semiconductors, the energy levels can be shifted towards one another by atomic substitutions, thus reducing the band gap engineering. In contrast, band structure modifications by blending organic materials can only shift the energy levels concertedly up or down, and this is due to the strong Coulomb effect that can be exploited in organic materials, but this has no effect on the gap. It would be very interesting to also change the gap of organic materials by blending to avoid the lengthy synthesis of the new molecules. The researchers now found an unconventional way by blending the material with mixtures of similar molecules that are different in size. The key finding is that all molecules are arranged in specific patterns that are allowed by their molecular shape and size. This induces the desired change in the material's dielectric constant and gap energy. The researchers were able to clarify the mechanism by simulating the structures of the blended films and their electronic and dielectric properties. A corresponding change in the molecular packaging, depending on the shape of the blended molecules, was confirmed by X-ray scattering measurements. While this proves the feasibility of this type of energy level engineering strategy, its employment will be explored for optoelectronic devices in the future. Good day, this is Professor Will, CBMD PhD, on microbiology, bioinformatics, and pathophysiology. This video was created for educational purposes only. Hope you enjoyed listening. Until next time, have a great day.